Thank you. Yeah, so I'm here to talk to you about weather forecasting. This is broadly how this is going to go. So I'd love to tell you what is weather and what is forecast. AI is good at it, and it's really interesting, but why and how, we'll dive into that a little bit. I'll take you on a little bit of a journey to how we got to the best models that we have at the moment. And then also, where is this all going? Where might we end up? So this is me. Hi, I'm on the slide. So this is a little bio. So I'm currently presenting at Python Science, as you can see. I think pretty much all the other things Jesse told me. I just really wanted to show this off. Did you know you could do this on Keynote? It's kind of crazy. Cool. So my credentials to talk about this. So my background, obviously, at CERN. Didn't do much weather there. I did experience some, though. I'm now working, so I'm at the Alan Turing Institute, and I'm working with the Met Office to design something we're calling FastNet. I think there's some kind of meteorological pun in there. So if you know that, that's great. And we're really trying to target this big thing of can we get a really good global weather forecast? And I'll tell you maybe why that's interesting in just a little bit. Here's an example of me presenting the weather. Alex Deakin, definitely my name. These definitely real places and real statements about the weather. So yeah, this is because we did a visit to the Met Office and they let us use their studio. Yeah, it's really hard you have to stand in the spot and you have to look at a video of yourself doing it, like mirror inverted. It's like genuinely quite hard. I don't know how they do it. Cool. So, quick disclaimer about this talk. I think you should be really skeptical of AI everywhere, especially in science. And I know that's like a bit of an antithesis here, and we've had two really great examples of how it is used. But the benchmarks that people often test against with AI are really not well tuned, and so you often have like a positive result that actually needed experts in the field to compare to, and it wasn't very well calibrated. So, but I do want to tell you about weather because it's a bit of an exception because we have really good baselines in weather. What is weather? Well, anyone want to tell me what do you think weather is? Any guesses? The rain, maybe. The sky, the wind, the temperature. It's all of that kind of thing, right? So if you Google weather, that's what it tells you. So temperature, precipitation, and wind. Rain is cool kids call it, I guess. So that's great, and those are three things I experience when I go outside. But weather is a very, very complicated system. It's at least that complicated. So there are lots of different variables you can imagine, like measuring things like the pressure, the wind speed, like solar radiation, forecast albedo. I don't know what that is, but it sounds spicy. Temperature and all of these things, temperature and wind speed, they exist at different height levels as well, because there's the wind that I feel as I stand outside on Camden, and there's the wind I feel when I'm sort of leaning out the emergency exit row seat on the airplanes that I take. Very different forces of wind, right? Cool. So this is when I say weather, this is what I mean. I mean all these things, and usually that data exists on a sort of grid around the Earth. So where does weather data come from? A couple of different places actually. Not as much hospitals, but definitely planes. So planes have a lot of instruments on them to pick up these kinds of readings. They have radar sensors. There's satellite. There's ships, there's buoys, weather balloons. I think community projects exist to launch weather balloons up into the sky and provide readings. And to get all that data to be on that uniform grid that we saw earlier is actually a non-trivial task, and a lot of thought has gone into how to do that well. That's called data assimilation. So that's how we get there. Now, why care about the weather? Well, the obvious reason is I need to know when to go to the beach. I need to go when to book my day ticket return to Brighton and hang out with this seagull. I think that's a super important reason to care about the weather. I mean, obviously this is not the reason, right? I feel like weather is often perceived as is it going to rain tomorrow, right? That's generally what we care about. But obviously, I had a lot of fun with animations in this talk, by the way. The world is on fire. Did anyone notice? Yeah, this was 2 years ago. We had 40 degrees a couple of days in a row. There's hurricanes. There's really dramatic extreme weather events. And genuinely good weather forecasts can save lives if you can tell where a hurricane is going to make landfall. You can, if you know that sort of 5 days in advance, you could save a certain percentage more lives. So it's really important to be good at this stuff. So it's not just for show. And what I'd like to tell you is, AI forecasts are kind of better now than like physics-based forecasts that we solve on a whiteboard and with big supercomputers and stuff. There's an asterisk, and I will get back to that in a moment because AI, as you know, has its caveats. How did it get good? Well, the main reason, just like ChatGPT and things like that exploded in how good they were, it's largely due to data availability. So ECMWF, the European Center for Medium Range Weather Forecasting, say that 5 times fast, they released a lot of historical weather data, something from like 1979 all the way to like 2023 at hourly timestamps on that grid all around the world, and 72 variables for each grid cell. So it's a ridiculous amount of data. For context, 9 petabytes, by the way, that's like what? Like 9,000 times 1 terabyte. A terabyte is like what you'd get in a good laptop. So imagine like 9,000 really expensive laptops. That's how much data we have. And AI does a great job with lots of data. So the maybe not really part, I think it's good to get this out the way. So if you imagine, the distribution of like types of weather that you might see, you can imagine the sort of top of this being, the vague trends that we see on our apps, right? Like, oh, it's probably going to be sunny or rain in Camden, right? It's a bit windy on the the Balearic Islands, right? Like this kind of vague, big weather pattern makes up the majority of what we see, right? Like a big thing of cloud will cause, like less temperature. It dominates the amount of weather, like especially historically. But sort of at the edges of like this distribution of weather, you might science people like to call this like the tails of the distribution. So where there's not much, activity, but it does exist, are things like extreme weather events, like typhoons, hurricanes, droughts, monsoon, all this kind of thing. And it's really like, this is the hard part, but it's the most important part to get right. And this does not come for free with AI is the sort of main message I wanna let you know, but then maybe some of the other things that I will show you will make you surprised, because I think a lot of people in this field have been very surprised about how good things have gotten. Quickly going to tell you what I said. I'll tell you like what is forecast. Forecast is like the question of forecasting. If I know the state of the weather right now, what is the state of the weather in like X hours? That could be like 1 hour, 6 hours. It could be like 30 minutes, like 12 years. Just some question about like how far forward, like what will the weather look like as we sort of go forward in time. What weather forecasters do, both AI based and physics, and maybe you just having a punt at it at home. You'll generally have some model, some system that takes in state of weather and then spits out state of weather. So that could be a physics model or an AI model guessing on vibes. Like it could be anything, right? Like as long as you're able to produce something that looks like the thing that came before. Actually, quite a common baseline in weather prediction is this thing called persistent, which is just we're going to assume this is the weather like forever, and at some point, obviously, you want to do better than that. But it's actually pretty good for like short time horizons, right? Because like it doesn't change that much on a short time scale. But the way you sort of make a forecast is you take this output of the model, and then you say, okay, this is now my new input, and I'm going to forecast again in the future. And so, this is the real weather that I look at now. I put that in my model. Here's my predicted weather at 6 hours. And then straight away, I take predicted weather at 6 hours, I put it in the model, get predicted weather at 12 hours. And I can do that over and over and over again until I get like my weather at whatever timescale I want. As you can imagine, these forecasts get less and less accurate the further away from now you get. So that is how forecasting works. So this plot I dug up for this talk. It's a very I think it's quite a confusing plot, so I'll try to guide you through it. This is just a sense of like how good is weather forecasting, right? Like how good are we at that task? Forget all the AI stuff. So people like to say this line, which is we've gained 1 day of weather accuracy in like every 10 years. And what does that mean? So here we have sort of 4 lines of of weather forecasts, and these are like over the different years that we've sort of done them. So, like 1984, like this is the best weather forecast for, I think that is 7 out to 7 days averaged across all of the days. in 1984. Here's our best attempt with all the new science and PCs we've made in 2016. As you can see, it's better than it was here. And I think every sort of 10 years, what ends up happening is the curve here starts to match the forecast from the curve above it. And the curves above it are shorter timescales. So this is the 3-day forecast, which is so much easier to be good at because the weather 3 days in the future, much easier to predict than the weather 10 days in the future. So that's where this phrase comes from. It means that we're doing better and like sort of by like, you know, a day at a time every 10 years. So this is like really quite cool. It's a very clear indication of scientific progress. But could it be better? So, I mean, the whole point of this is probably yes. And let's see how AI models compare at the moment. Any speedrunning fans in the crowd? Okay, not the right audience to pitch this to. I like watching speedrunning videos. There's this creator called Summoning Salt who shows them from the perspective of here's the current world record, and then someone found this crazy trick where you can, glitch through the floor in Wii Sports and then hit like 20 home runs at once, and that's how the world record got reduced. And I'm going to do the same for weather forecasting. So I'm going to show you this plot a couple of times. This is a plot of just some like a selected weather variable that people often compare to. So this is something called the geopotential, which is like to do with the height at which certain bodies of pressure sit. We can talk more about that later if you'd like. But the point is it's just like some aspect about the weather that we often compare to. So this is up into sort of about 2021. This bar at the top is basically the best physics-based weather forecast. So if we get here, it's relative to that. So as soon as we cross that line, like we're seriously in business. Like we're doing better than the best efforts over like all that time, all of that like physics like sort of iteration that we had. So we're about 60% as good, sort of around 2021. It's fine. We're not really shouting about it. It's like, okay, it's about half as good as my physics forecast. Who cares? Certainly not me. But then this happened. Okay, and by this I mean him, and like he is him, because this is Ryan Keisler, and I had never heard of this dude. But as soon as I sort of got into this field, like he wrote a single author paper, affectionately still uses we, which I think is so cute. It's like you and what army, scientific objective language and all of that. But yeah, he by himself, let's be clear. Trained a model sort of from scratch that became almost as competitive as 80% as good as a physics weather forecast. This jump was huge sort of for its time. So what did he do? This is a tweet from the previous guy saying Ryan's model defied my expectations of how good purely data-driven models could be for medium-range prediction. This is super exciting and raises the question, what's next? Well, what did he think of that was so interesting? Like what made this jump so effective? So weather data, by the way, really dense. The thing I showed you was a very much an oversimplification. The sort of the grid around the world. It's actually it's more like that. So it's like in every one of these dots, just to remind you, 72 numbers at each dot, and that's just one time step. It's just so much data. So Keisler's idea was sort of replace this with a simpler structure. I know that doesn't look that simple, but it's way simpler than what I just showed you, and then learn all the physics on the simple structure instead. And basically what you can do is, find an intelligent way to encode that data onto this simple structure, learn all your dynamics, process your dynamics with machine learning on the simple structure, decode it back to the Earth grid. To roll out the forecast, as I showed you earlier, you just do the same thing over and over again. This is using something called graph neural networks, definitely either a question or a topic afterwards. Really just smash the field wide open with this, And so here are his results. So these are different variables. These are weather speak for things like temperature, wind speed, humidity, geopotential, all of that stuff. I think they're very pretty pictures, but I think what's quite clear is the large-scale patterns by Ryan's model. I think we're on first name basis, me and Ryan. Ryan's model, Dr. Keisler, are they're really matching up quite well, and this really just this blew this whole thing wide open because people are like, okay, we're in the age of AI now. Let's scale this up. So what happened next? Google threw a bunch of money at it. So and the sort of dot here called Pangu, which is, I guess, I don't know if that takes inspiration from Pingu. I really hope it does. That's from Huawei. So like tech companies put their money in the game, and they overtook this line, and it's really just so impressive because the physics models are so good. So this is like Google did this. So I showed you a simpler shape before. Google took that shape and made it really complicated. So the main difference that I'll try and guide your eyes to is like, so this dot right here with all the arrows pointing to it, what this is trying to show is that like DeepMind like stacked these shapes of increasing complexity, but sort of kept the edges of the previous shape such that you sort of, these long-range connections that like come from halfway around the globe are allowed to influence like any particular point. And the intuition there is like, okay, I'm going to give my network a chance to think about like, if it's sort of sunny in Arkansas, I want you to sort of take into account that like it's raining really, really hard in like, I don't know, like southern India, right? So like that's the kind of thing that, 5 days ago weather somewhere else is somewhere, and it's like someone else's weather in 5 days, right? So that's sort of the idea. I really think the main advancement though is just the way they scale things up in the very AI sense of it. So same amount of data, but training for longer, larger model scale. And other tricks that that are really, really, really cool actually. So that's how they sort of did it. And just to show you that this isn't like all like hearsay and stuff, here's a real example. So this is Hurricane Beryl. And this is a rare case where the AI model, so GraphCast, predicted the landfall of this hurricane in Texas like 7 days out before it landed. And it was different from the European and American 5-day forecasts that predicted that it would just sort of peter out in Mexico. So this is an example of like a real event that affected real people where the AI was able to alert emergency services a lot earlier. I don't think this would have been like taken seriously at the time, so I don't think this probably produced any like real impact on the ground. But if these forecasts were in production, this is the kind of thing that could be possible now. Like extreme events are suddenly like AI is starting to get really good at them, right? And I said it didn't come for free, so that's really, really quite impressive. And there's been a little bit of progress since then, right? So this was 2023. Then a bunch of people tried their hand at this, and like lots of people were able to reproduce with different architectures, different ideas, data-driven systems that were able to rival the best we can do with physics. And that's like really just, I think I still find it really shocking. Like it's so much expertise, so well calibrated, these physics-based models, and AI is really starting to do well. So one thing I'll quickly talk to you about just in the last stages of this talk is like the things AI tends to get wrong. This is actually some plots from a project I did on forecasting like satellite images of clouds. The thing on the right is the AI model we ended up using in production. The left is sort of like the true picture. And you can see just like Ryan Keisler's plots, like the AI often hedges its bets on what it's guessing. It often like smears out these features. So it's right on average. And this is a feature of a lot of AI models and often inherent to how they're trained. When you calculate this like loss function or reward function that tells the AI, okay, how do I change myself in order to do better? You're averaging over the whole globe, over a bunch of data, a bunch of years, all at once. So you're going to lose that fine scale information. And I wanted to show you some of the things that do better at this. So there are techniques that seem to do better in particular. So as you can see, this is very much this is a cat-shaped cloud because this is obviously a weather talk. So I wanted to tell you like 1 minute about like diffusion models. So you might have seen like these image generation things like from as early as like 2 or 3 years ago, where like you could type in some text and generate like a really high quality image. Well, diffusion models are like behind a lot of that sort of like image sort of modeling revolution in that field. And the way they sort of work is you sort of show it an image at training time. You progressively add noise to the image, and then the network learns to like subtract the noise that you added. And sort of miraculously, what this does is it's able to add like finer and finer details as it does this sequentially. And what you end up getting is something that is able to model, like this step to this step. You can see there's like a lot of fine details to the picture that it's able to sort of get right. So this is a really interesting technique that's actually proving very useful for weather forecasting. Here's an example. This is something called GenCast. This is another effort by Google DeepMind, who's been a real sort of player in this space. What they're showing here is, that they're taking different samples from their AI model in slightly different situations, and sort of forecasting the path of a cyclone. In all of these cases, the width of this distribution of guesses that the AI model is making is sort of roughly centered around the real path of this cyclone. And the closer you get, so here's 7 days out, 5 days out, they're actually already coming quite close to where the cyclone really went. And then 3 days out, 1 day out, it like completely zones in. So we've even got this notion of like probability that comes with diffusion models. Like this idea of like a spread of possible scenarios, and that's really useful for forecasters, right? Because then you can prepare for like the worst, right? You can say, okay, here's 5 things, like these are probably the most likely events, and things like that. So that's really cool. I'll sort of quickly tell you this because this is probably the best thing we have right now in forecasting, and this is a method that sort of incorporated all these advances in physics equations back into the model itself. And what that ends up doing is basically saying so it still learns physics just like GraphCast, just like a lot of the things I've shown you. But the difference is because you put actual physics equations in there, when you train this model out, and you forecast out to long timescales, it's still going to look a lot like actual physics. And a lot of these AI models don't do that. They totally blur out, and they're like, we don't really know, so let's try and get it on average. So incorporating, physics as part of this process, is really useful, and it also sort of brings back some of that explainability, this gray box thing that we talked about earlier. And just really quickly to guide your eyes to what that looks like. It's really hard to see, I think, from this distance, but there are 3 columns of this plot that I really want to show you. This is sort of some data from this big Era 5 data set I mentioned earlier. It has some complicated weather patterns for the humidity. And basically, this is pretty detailed. This is the neural GCM, so the physics sort of informed approach. And what it's able to do is retain a lot of that small scale structure, and only until you get to the sort of 10-day mark does it start to sort of lose that detail. Compare that to GraphCast, the previous best AI forecast, and it's totally blurring out this detail, even at the 5-day horizon. Compare this to this, you're losing so much detail, and that's that will impact things like the specific location of is it going to rain in Brighton for me to book and meet my seagull? So really, really cool that this is sort of developing, and I think it's a really promising direction. So I'm very quickly going to tell you, where is this all going? What's next, right? If this is what we have now, what's next? Well, the future is kind of now, in a way. So ECMWF, they make the best physics weather forecast in the world right now. And they have just said, this was I think about a month ago, they are running side by side in production their best AI model with their physics forecast. And I just think this is incredible, right? And they've said themselves, it outperforms traditional models for many measures at the fraction of the energy use. I know it sounds it's really hard to not sound preachy with this stuff, but it's just it is kind of working, and it's kind of this is a massive endorsement, right? They really know their stuff. They are producing the best physics forecast. So if you don't believe me, believe them. So the last thing I'll talk about is I kind of alluded to it briefly. This step of taking all of these measurements from ships and weather balloons and planes and satellites. There's this data assimilation step where we make that look like this uniform grid. And really, this is kind of just an artifact of how we produce forecasts with physics-based models. We often run those on grids. That's just an easier way to think about life in sort of a well-organized, neat grid. But really, we don't have to do that. So what if we skipped all of that complicated step, all of the those complicated steps, and we had a model take in all of those observations, just by itself, and then immediately spits out a forecast. So you're basically allowing the model to learn directly from these observations, and what that will do is it will really help regions for where there might not be, I guess, that much data historically, because you're not kind of in this grid we have to interpolate over regions that we don't have data for. We have to kind of do a mathematical guess, and that means that a lot of that data could be really rubbish. Specifically, I think rain in Africa is like notoriously so bad in like this data set that I mentioned. So it does have some caveats, right? So if we're able to go direct from observations, then we're not making funny guesses about those areas. We're just using the data that we have, and we'll just say we don't know in other regions. So that's happening. There's some work actually at the Turing happening with that. We can talk about that later if you'd like. This is one last big slide. I've stolen this from someone from ECMWF. They're presenting this at CERN, I think. Yeah, they presented this yesterday, so it's really, really fresh. They want to build something like called a weather generator, which sounds really dystopian, actually. Maybe that's what they used in Dubai to see the clouds. Satellite data, reanalysis data, like climate simulations, like so much other, like there's so much data I haven't told you about. They want to use it all, everything, and train one model, and then deploy that model for many different weather tasks. So not just predicting 15 minutes ahead, not just predicting 3 hours ahead, but predicting into days, in decades, in like making climate forecasts. You know, how's the world going to change with climate change? What's the extreme event risk? What's the energy output, like in terms of solar panels? They kind of want to, you know, do this at a massive scale. Can we get everything at once? I don't know if this will work, but like, you know, the trends are positive, and you know, as you can see, AI can do really well with some of these things. So I think this will be really interesting to see if things like this pan out. So this is my last slide, some closing thoughts. Get ready for the skid animation. Here we go. AI is really good at weather forecasting with huge improvement over the last 5 years. Thank you, ECMWF. Era 5 is an amazing data set. Models run really fast at a fraction of the energy cost. Ryan Kaiser, the GOAT. Can we all agree? Fucking let's go. Fine details and extreme events are really important, and we have to get those right. And models are getting better, which is just so incredible. AI forecasts will soon be used for real forecasting, as you saw, and maybe even on your phone. Who knows what will happen there? Please don't give me control of Keynote animations, and you can find me on Blue Sky if you want to chat more or in person here. Thank you very much.
But Nathan, aren't these AI models really bad for the environment?
Thank you for that really not planned at all question that I definitely don't have a slide for. Wow, oh my gosh. So AI for the environment, right? I just really wanted to show you this too. Thanks, Jesse, for asking that. So yeah, okay, I get it. AI, stop training your AI models. You're burning a bunch of CO2. It's not going to be good, right? Totally agree with you. One thing that does seem to come out of this, though, actually, before I tell you what comes out of it, let's just look at some figures. So this is the same graph I showed you before, like the performance with the sort of years when they generated the models. But I've made some blobs, and the size of the blob is how much GPU power they used to train it. So Keisler did this whole thing with about like 10 days on one GPU. So one GPU running continuously 24 hours for 10 days. Obviously, people generally run on multiple GPUs. One GPU for 10 days is 2 GPUs for 5 days. And the biggest model, so Neural GCM, it's like 55.6 GPU years of compute. And isn't that just unfathomable scale, right? Like the author of that paper said in an interview, if you're watching this, Stefan, I love your work. Please don't come after me. But you did say that scaling this model further to like more dense grid would be expensive even for Google. Even for Google. That doesn't mean anything to me. So that's just, so I totally get behind that. One thing I will show, and here's an example with Neural GCM, is that I kind of glossed over this, but like what you're seeing here is the amount of weather forecast days simulated with like real-time seconds of runtime, as you can sort of see here. This is like minutes. This is like a state-of-the-art weather forecasting thing. As you can see, this is 13,000 CPUs this is running on. We're not even at 0.1 days. Bro is lagging. But like the sort of inference time compute, it's like 4 orders of magnitude better at inference time. In the time it takes to run like a 6-hour forecast, like this might take like an hour. And in that time, we could run like thousands of simulations of possible climate and weather scenarios. So both in terms of emergency response time, Jesse. Well, I know you're super interested in this question that you definitely asked. Both in terms of like emergency response times and like actual savings of like running these models in practice. There are definitely some massive gains. Whether they, recover 55 GPU years, I'm not sure, but I think that there is some grounds to say that. So yeah, I just wanted to mention that.